Okay, hi everyone. Thanks for accepting the paper to be here. So I'm Martha Lewis, and this is joint work with Yared Al-Mahiri, who I thought was going to be here, but I guess isn't, and Bob, and it's actually based on Yared's master's thesis, a lot of his work. Okay, so the main question that I want to look at today is how symbolic representation reasoning can be accommodated within some sort of distributed or connectionist architecture. And we're going to look at these two different approaches. So the first one is by Smolenski and Legendre, and they have this view of cognition that they call the integrated connectionist symbolic architecture, which I'll call ICS. And this approach does have some limitations, which I'll go over in the course of the talk. So Bob Cooker, in 2011, together with Manoush Sajzadeh and Steve Clark, put together a model called the Categorical compositional distributional model. And that does something similar, but we're going to try and integrate the two models and take the best of both worlds, essentially. So going through the ICS architecture. So Smolenski's aim is to look at how we can implement symbolic reasoning within a connectionist substrate. So we build this up hierarchically. The first level is just a set of things. And so symbolically we'll call that an F, and in a connections model we can represent that as a set of a filler vector. So each object is represented by a different vector, and if you've just got a set of objects, you can represent these just by adding filler vectors together. However, if you're interested in the order in which these things come, which, for example, in language you might be interested in order, you can't simply add vectors together because addition is commutative, obviously. So the idea is to bind a filler to a role. So in the symbolic notation, we've got this sort of slash notation here. And this gets implemented in the vector notation by taking the tensor product of a filler vector with a role vector. And then to add more structure into this, so for example, if we want to start looking at trees, which again for language is going to be really important, as Stuart Hameroff was talking about, we're going to need to start generating more complex roles that can be added together to form a tree structure. So I'll give an example here. So we've got a sentence. So let's say we're interested in representing a sentence. And I've written there S. So S is the sentence, starts here. We've got an NP, stands for noun phrase, on one side. And on the other side, a transitive verb and another noun phrase. And so that tree is just what this bracket notation here represents. Now, if we want to represent this within Smolenski's vector notation, we have a noun phrase on one side, so that's noun phrase tensored with R0, which is one role. Let's just say it's the left-hand role. And then something here, which I won't go into that yet, tensored with the right-hand role. So R0 is the left-hand branch, R1 is the right-hand branch. Then we can multiply this out, and we get that we get one vector here describing the sentence, where these roles are complex. They've or complicated rather. The roles themselves are structured. And this notation here is just notation for R1 tensor R1. So this is how Smolenski proposes to represent trees within his formalism. Now the problem here is that trees are going to inhabit an arbitrarily large space. So if we have a vector at depth d, we can think about a vector space SD, which is formed of vectors of this form, a filler times some kind of branching, and we're then going to need the direct sum of all, well, of as many depths as you need in order to represent the tree. So we need an arbitrarily large space. Also, it's not totally clear how you would compare two different sentences there. So if you've got a sentence with different depths which inhabit different spaces, it's not totally clear how they compare. So, in contrast, we use a formalism called Categorical compositional semantics, which actually was originally developed off the back of some of Smolenski's work. So this framework provides a general program for mapping some chosen syntactic structure, that's your tree representation on the one hand, over to a semantic representation framework. For the syntactic structure, we use pre-group grammar. So you don't have to use pre-group grammar, there are other types of grammar that you can use. A pre-group is a partially ordered monoid where each element in the set P has a left adjoint and a right adjoint. And those adjoints, you can kind of think of them as inverses. So we've got this, the PLP sort of cancels out to 1, and similarly PPR cancels out to 1. And you can use a pre-group over whatever set you want. So we're going to use it over the alphabet N and S. So N stands for noun, S stands for sentence. And a transitive sentence is typed like this. So what's going on here is that we've got a noun here. This concatenated type here, NRSNL, is the type of a transitive verb. And then you've got an N here. And according to these rules, the N's cancel out with their adjoints on each side, and we get left with an S. So what this is saying is that this is the type of a grammatically well-formed sentence. This string here is grammatically well-formed according to the rules of grammar because it reduces down to an S. So, I won't go into loads of detail, but just to give some other examples, that was a transitive verb, so that's like likes, for example. You can also have intransitive verbs, like runs. So an intransitive verb has type N, NRS. Then if you've got John runs, these guys cancel out, and we get left with an S. Similarly, you can have an adjective, which has type N, NL. And then you've got, so this might be yellow car. Then these guys cancel out, and you get left with a noun. So we've got this grammatical type, this grammatical category. We need to map it across to some sort of semantic representation. So the semantic category we use needs to be compact closed, which I'll go into in a minute. and we use finite dimensional real Hilbert spaces. Again, there are choices for this. So one choice is to use the category of sets of relations. Another thing that we're looking into at the moment is to develop a formalism for Garden-Force's conceptual spaces that also fits into this compact closed category. So within a compact closed category, we've got these morphisms here, which send objects of this type to the identity, and similarly does type introduction, which sends the identity to tensor product here. What these guys are is actually these cups. That's the epsilons, and the etas turn into caps. The snake equations are equations which say that if you have three types and connect them with a cup and a cap, then that's equal to the identity, and then also equals, I've got to do it the right way around, yes. So in finite dimensional Hilbert spaces, and we just work with real numbers, the adjoint objects are equal to each other, and they're also simply equal to the original vector space itself. And given a chosen basis for a vector space, we have the morphisms look like this. So epsilon sends a tensor product of two vector spaces to just the real numbers, which is the unit object in FL. And what this does is take a tensor a rank 2 tensor to its trace. So it's basically just mapping a matrix down to one real number. Similarly, the type introduction morphism eta maps the unit to a matrix by taking 1 to the diagonal matrix formed of the tensor product of the two of matching basis vectors, essentially the identity. So these so what this really implements is tensor contraction when it actually is used in a sentence. In our pre-group category, the tensor product is concatenation. So here, this this concatenation of types is equivalent to the tensor product, and the eta and epsilon morphisms are the unique morphisms that you get from these inequalities here. So in order to map the grammatical reductions over to the vector space, we use a strong monoidal. We define a strong monoidal functor that takes the noun type to a noun space and the sentence type to a sentence space. So the noun space in distributional, if we think about distributional semantics for a minute, the noun space is generally formed by generating a set of word co-occurrence space from text corpora or something similar. The sentence space is slightly more difficult. So a very obvious choice for the sentence space is just to take 1 and 0. It's very boring, and that just maps into true and false. Ideally, you'd want to take something more interesting. So again, composite types are then constructed using the tensor product. And then given a set of word vectors with a particular types and type reduction that maps to the sentence type, i.e. you've got a grammatical sentence reduction, the meaning of a sentence in this sentence space is given by the mapping to the vector space. So graphically, we've got this transitive sentence reduction here, and this maps into a vector space reduction here. So this triangle here represents a state in a vector space, which is just got one line coming out of it, which means it's just a vector. Similarly here, the triangle with 3 lines coming out of it is a state in a vector space formed of the tensor product of these vector spaces here. So it's a rank 3 tensor. And then what these cups are doing is tensor contraction on these parts of the tensor.
And the result is a vector or a tensor?
Which bit?
The result when you perform.
Oh, the result is just a vector.
A vector, yes.
So a single line is essentially, you can think of a single line is a object which is a vector space, but because it's got the triangle on the top, that makes it just a vector. Okay, so we want to map the Smolensky's model over to the model I've just described. So in Smolensky's model, we have vector spaces that look like this. However, in both cases, we are actually working with vectors and linear maps. So there should be some sort of mapping between the two. In Smolensky's book, we have that this representation can actually be written as some kind of matrix multiplication times a direct sum of filler vectors. So in the categorical compositional model, we start with a tensor product rather than a direct sum of vectors. So in order to match these two things together, this on this side, this is the ICS model, put a direct sum of filler vectors, pop it into some matrix, and out comes, this ought to be a really thick line, because it's actually one of these trees in one of these unbounded vector spaces of unbounded size. So this is a really large thing that's coming out of here. In contrast, what's happening in the categorical compositional model is, supposing we start with the same direct sum of filler vectors, map the direct sum to a tensor product just in the obvious way. Then we get a sort of set of thin lines coming out. We can then apply the linear maps that I described on the previous slide, and we come out with just a single vector in a sentence space. So the ICS model has been designed to work within a cognitive architecture. And so we want to use the ideas from that in order to develop our model, which was originally developed just for natural language processing, into a cognitive system. The ICS model also has a notion of approximate grammatical parsing, which at the moment we don't have at all. We've just got that it's either grammatical or ungrammatical. We should be able to allow richer representations as well, taking in other So as well as just word co-occurrence, there should be sort of input from cameras or smell, something like that. And people have implemented something really similar to Smolenski's model, and this should be able to provide us with a starting point for developing this categorical compositional cognition model. Just a couple more things. So Smolensky and Legendre have the idea of semantic roles. So they're, instead of roles simply being places in a tree, you can also have roles sort of carrying some semantic content as well. We can take account of this in quite a simple way just by redrawing the diagrams, which we're allowed to do. Well, there is a specific reason why we're allowed to do it. And then getting this sort of semantic role vector here, which gives us out the sentence. And then more complex semantic roles we can implement recursively, so we add these semantic roles in at the requisite time. I'll skip over relative pronouns for now. One thing we need to do with this is to show how fillers can be unbound from roles, because roles provide a structure. You might want to unbind a filler from the role and move it to another place in the structure. We need to use some sort of approximate notion of unbinding, which we can do. So within categorical, compositional, distributional semantics, there's a number of useful structures. So we can do ambiguity between meanings. We've started looking at entailment, and also relative pronouns, which allow us to form definitional noun phrases. And we've also got notions of over and under extensions of concepts. So bringing all this into being Smolensky's model could provide some useful input, I think. Okay, so in summary, we've provided this mapping from the ICS formalism to the categorical, compositional, semantics formalism. So that allows all these sentences to be represented within this finite shared meaning space, but yet within some sort of connectionist substrate. Further work, we need to look at the grammatical matrices that ICS use and see what sort of structure we can take from those and show how that maps across to compositional semantics. Similarly, compositional semantics doesn't have really a notion of knowledge update as yet, so that's another area we want to look at. And on the implementation side, these models that I mentioned already use tensor product representations and provide an ideal substrate to start implementing a computational model of this. Thank you.
I would like to ask about the empirical impact of the model. At the first look, it looks like a Montague that goes quantum.
A Montague that goes quantum,
yes.
yeah,
that's a good idea, but it's also problematic from an empirical point of view.
Right.
So, let me ask a concrete question. Many people have investigated with such tensor models adjectival modification.
Yeah.
So the basic puzzle, if the color of a red nose is different than a red bean or a red flag.
Yeah.
Right? And in your case, I think you have a vector for red, a vector for flag.
Yeah, so
and then the modification is a vector or a tensor?
The modification is it's a rank 2 tensor matrix.
Aha, then because Lapata has treated such problem, then it becomes a vector, and she could talk this typicality puzzle. But when you have a tensor, then it's different.
So actually, last year at this conference, I presented a paper on how to deal with the pet fish problem.
I see. Yeah, it's
within
the
this,
same. Yes.
within the distribution categorical
Aha.
distributional semantics model, and that works quite well. And I think the reason why it works is because you do get a lot more information within the matrices than you do in the vectors. You can encode correlations between attributes, and this is why.
We have a paper about pet fish.
Yes, it's in the proceedings of last year's CR.
Questions?
I've got to ask this since you're from Oxford. Like if you're looking at Sampson's contextual semantics,
Yeah.
I guess he would say that you've got this grammatical structure and you've got this part which would be the local sections.
Mm-hmm.
And then the problem to come up then is do you have a global section that corresponds to, I guess, the interpretation? And this asks the question: is is that always the case in the compositionality? You assume there's always a global section.
Yeah.
Hence, language is always contextual, non-contextual.
Yeah. At the moment, we are looking at that. So yes, what you might want to say is that. Okay, so a very sort of engineering-based answer to this is that at any point you're only concentrating on some kind of small domain that you've sort of specified in advance. So if I'm talking about fruit, I don't care about functors, for example. Then, of course, the question is, which I guess is what you're coming to, is there a big space where I can project down to dialogues about fruit and project down to dialogues about functors, and all of this is non-contextual. I don't know. At the moment we do just look at small.
Because I was seeing some work on garden part sentences.
Oh yeah.
And so there is this thing. It's almost like cognitively the subjects actually then they have two parse trees remain.
Yes.
And so that's, I think, very aligned with Sampson's view. In that case, they do not construct a global section.
Yeah.
And so in that sense, it would be contextual.
Yeah, so with the garden path sentences, the other way you can think about it is that you've actually got a sort of ambiguity in the parsing.
Yeah.
And you've got two things there concurrently. So we can model that on the semantic side. We don't look at the syntactic side much at all, other than choosing a grammar and using it. On the semantic side, we can model ambiguity, so by using density matrices. So we have some kind of, let's say we've got a vector for bank as in river bank. So bank, river, and bank, river, and then you add that to bank, financial, and then so yeah, if you obviously put the right sort of coefficients in front of these. So you've got this density matrix, and this can encode, well, it obviously encodes ambiguity between these two different meanings of the words. And there's been some work done on this, where we encode words in this way, and then depending on the context, so if you say, I sat on the bank, then the meaning collapses down to this meaning. But we haven't done that at the syntactic level yet, only at this semantic level.
One last question. Okay.
I'm hoping this is just a yes question. Are the nouns on the left and nouns on the right spaces that you used for adjectives, are they naturally isomorphic to one another? Or?
Yeah, they're the same space in fact. So for adjectives, So so in the syntax it has this type. In the semantics, because we're in finite dimensional vector spaces, we basically have this, but the adjoint is the dual space, which is actually just the original space.
Okay, that's fine.
So they're identical.
The reason we're asking is just word order. You want rouge and red to have the same meaning, but you want to be able to have van rouge and red wine.
Yes. I mean, yeah. So there you'd probably use, you'd just say that an adjective in French has this type. I mean, we don't, the syntax obviously changes from language to language, so we don't assume that they've got the same type. But yeah, so there are some places where it's the same, which it might be interesting.
It'd be nice if it just fell out of the
It
theory
would
that
be,
all you
yeah.
have to say is
Yeah, that
rouge
would
and
be
red
nice.
kind of correspond and the
Yeah.
rest just happens.
Yeah, that would be good.
All right, thank you very much for your talk.